Good morning, my dear students. We had been discussing about stereochemistry, and in the previous class, we have discussed about the conformations and projection formulas. We have discussed the conformation of ethane molecule. We continue our discussion with the topic stereochemistry. Now we discuss about the conformations of another molecule, that is butane. Butane is CH3, CH2, CH2, CH3. So when we consider butane, all the carbon-carbon bonds are single. Hence, infinite number of conformations are possible. But we give importance to the rotation around C2 and C3 carbon atom. See here, this is butane molecule and this is the C1 carbon atom, C2, C3 and C4 carbon atom. So we think about the C2 and C3 carbon-carbon single bond. This C2 and C3 carbon-carbon bond could undergo rotation so that different conformations are possible. So we have to discuss about the conformational isomers of butane molecule around the rotation between C2 and C3 carbon atom rather than any other carbon atom. See here, when we consider butane molecule, if we take C2 and C3, they lies in a particular plane so that the projection formulas could be easily represented by using C2, C3 carbon atoms rather than any other carbon atoms. See here, this is butane molecule and we are observing the butane molecule. See here, observing the butane molecule through C2, C3 single bond. That means C2, C3 carbon-carbon single bond. When I am observing through the C2, C3 carbon-carbon single bond, I could say the third carbon atom and the second carbon atom is in one plane. So I draw the projection formula, that is the Newman projection formula of butane molecule, giving importance or consideration to C2 and C3 carbon-carbon single bond. The third carbon atom and the second carbon atom are in one plane. So we are representing the circle. In the third carbon atom, it contains two hydrogen atom and a methyl group. See here, this is the third carbon atom of Newman projection formula. I have one hydrogen atom here, another hydrogen atom here, and this is the methyl group, that is the fourth carbon atom, CH3 group, methyl group. When I look to the second carbon atom, it contains two hydrogen atom and one methyl group. See here, this circle is the second carbon atom. It contains one methyl group and two hydrogen atom. So now onwards, we discuss butane molecule and its conformation only on the base of C2 and C3 carbon atom. So when we see a Newman projection formula of butane molecule, you should think it is representing the C2, C3 carbon atom. You got it? So that The first and the last carbon atoms are represented as CH3 group. Now this is the simple projection formula, that is the Newman projection formula of butane molecule. Now we know C2C3 carbon could undergo rotation. See here, this is the first carbon atom. Sorry, first projection formula. See here, this is a eclipsed projection formula. That means the methyl group of first and fourth carbon atoms are in one plane. One plane. Now, keeping this CH3 group, that is the second methyl group, as constant, I am going to rotate the first methyl group or first carbon atom. That means I am rotating the carbon-carbon bond between C2 and C3. So I keep the CH3 group of the second carbon atom as constant, and I am rotating the C2-C3 bond so that the first methyl group and the two hydrogen atom present on the second carbon atom will undergo rotation. See here, now the CH3 group is moved between CH3 group and H group. You got it? This rotation is possible so that I will get infinite number of conformations. So, along the C2, C3 carbon rotation, infinite number of conformations are possible for butane molecule. Among these molecules, the most important three conformations are gauche form, antiform, and eclipsed form. That we will discuss one by one. Now you take here these examples, these pictures. See here, C in the third form, again it is an eclipsed form. But in that eclipsed form, the CH3 and H are eclipsing. See here, in the first structure, CH3 and CH3, HH, HH eclipsing. But here, see in the third representation, CH3 and H is eclipsing. Again, it moves to another conformation where the CH3 group are in the opposite directions, exactly opposite direction. Again, the rotation is continuing and we are moving to another form, and finally it will come to the final form. That means keeping one CH3 molecule as a constant, we are rotating the carbon-carbon bond, that is C2-C3 bond, so that we get different conformations. Among these conformations, three conformations are typical. That is, one is fully eclipsed form, another is gauche form, another is antiform. So fully eclipsed, gauche and antiforms are the three extreme conformations of butane molecule. Take down. Now see here, we are taking the three extreme case. The first one is we are taking the antiform, anti-conformation of butane. See here, this is the second and third carbon atom. Second and third carbon atom. And you are seeing the molecule through this plane. When you look the molecule through this plane, the first methyl group is above the plane while the second methyl group is below the plane. That means the distance between the carbon atom of this methyl group, that is the last methyl group, and the first methyl group is maximum. And that is the anti-conformation. So in anti-conformation, the CH3 group, which are the bulky groups or big groups, are exactly opposite to each other, or exactly opposite to the plane of C2 and C3 carbon-carbon single bond. Hence, this is the most stablest conformation, that is the anti-conformation. Now move to the next one, Gauche conformation. See here, the observer is seeing in that particular plane, C2, C3 plane. When he is viewing the molecule through C2, C3 plane, the first methyl group is above the plane, while the second methyl group is perpendicular to this particular plane. Or we could say the distance between the carbon atom of this methyl group and this methyl group is less compared to the anti form. That means in Gauche form, the methyl group could be placed between the methyl group and hydrogen atom of second carbon atom. I explain again. The methyl group present in the second carbon atom is placed between the methyl group and hydrogen of the third carbon atom. Now moving to the less stable or least stable form, that is the fully eclipsed form. See here, you are observing the molecule. C2 and C3 carbons are in same plane, and the methyl group, two methyl groups are above the plane. Above the plane. So we could say this is the least stablest form among the three extreme form. That is the fully eclipsed. See why this is fully eclipsed? Because the methyl group of second carbon atom and the methyl group of the third carbon atoms are in same plane and the distance is minimum. Take down. Now see, this is fully eclipsed form. Eclipsed form. See here, from the projection formula, we are converting to Newman projection formula. So the CH3 group, the hydrogen atom and hydrogen atom of the second carbon atom is in one plane with the CH3 group, H and H of the second carbon atom. That means this is the second and third carbon atom. So this is fully eclipsed form. See, the blue color represents this carbon atom and the red color represents the back carbon atom. So this is fully eclipsed. Now see next one. That is the on of the Gauche form. On of the Gauche form. See here. In this case, this CH3 group is lying between the CH3 group and hydrogen atom. See here. From that wedge, broken lines and thick lines, you could easily make it out. So this is on of the Gauche form in which the CH3 group is lying between the CH3 group and hydrogen atom. And see the third one, that is the extreme case, that is the antiform. Antiform. Basically, antiform is a type of Gauche form. Is a type of Gauche form in which the bulky CH3 groups are on the opposite side. See here, the CH3 group in the first carbon atom is below the plane, while the CH3 group in the second carbon atom is above the plane. So the extreme 3 conformation of butane are fully eclipsed, gauche form and anti-form. Between eclipsed, gauche and anti, there lies a large number of infinite number of conformations which are possible due to the rotation of C2, C3 carbon atom. Take down. See here, I am giving you some of the projection formulas. The first one is fully eclipsed. See here, in that fully eclipsed form, the CH3 groups are in one plane. That means the CH3 group of the second carbon atom mask the CH3 group of the third carbon atom. Moving to the second one, that is the gauche form. See, I am rotating the carbon atom. Carbon-carbon single bond. Now the methyl group has occupied between the CH3 and hydrogen atom. So this is a gauche conformation. Got it? Gauche conformation. Now this CH3 group is again moving, so that the hydrogen and CH3 are coming above and below. That means this is an eclipsed conformation. This is a type of eclipsed conformation. See the difference between fully eclipsed and eclipsed conformation. In fully eclipsed, the CH3 group of the second carbon atom and CH3 group of the third carbon atoms are in same plane. While in partially eclipsed or in eclipsed conformation, see, hydrogen atom and CH3 groups are in one plane. Then we move to the next case, that is the extreme one, anti-conformation, in which the methyl groups are in the opposite direction. Again the rotation, carbon-carbon rotation occurs, so that we move to another eclipsed conformation. Got it? Then we move to again another gauche conformation. This gauche conformation on again rotation will give you the fully eclipsed conformation. That means from a fully eclipsed conformation, it moves to a gauche conformation, eclipsed conformation, anti-conformation, again to an eclipsed conformation, and finally to gauche and eclipsed conformation. See, in between these conformations, infinite number of conformations are possible. Here we are locating or presenting the conformation at 60-degree rotation. 60-degree rotation. So these are the conformations of normal butane. So as we were discussing, the same thing it is here. See, a fully eclipsed conformation or totally eclipsed conformation moving to 60-degree. See, the energy has decreased. The energy has decreased. See, the potential energy is maximum for fully eclipsed conformation. When it is rotated to 60-degree, it moves to a gauche conformation. See, the angle between the methyl group is shown here. And again it moves to a eclipsed conformation. So what happens? The energy is increasing, but the energy is less than the energy of fully eclipsed conformation. Got it? Now again I am rotating from 120 to 180 degree, so that it moves to anti. anti-conformation. See, the energy is minimum energy. Again, it is rotating through 60 degree so that it moves to another eclipsed conformation in which CH3 and hydrogen atoms are getting eclipsed. Got it? Again, the energy is more, but it is less than fully eclipsed conformation. Further rotation, it moves to gauche form. Again, finally, it reaches to totally or fully eclipsed conformation. That means from the conformations of normal butane, fully eclipsed have maximum energy. That means minimum stability. While antiform is having minimum energy and maximum stability. Gauche form have energy less than fully eclipsed but greater than anti-conformations. Very, very important. Take down. Now we move to the conformations of cyclohexane. We know cyclohexane is a cyclic molecule, and by convention we consider it as a planar structure. Planar structure. And it is having 6 carbon atoms, and all the carbon atoms are sp3 hybridized. There is no double bonds or triple bonds. That means the carbon atoms are connected to another carbon atom through carbon-carbon single bond. So we expect a bond angle of 109 degree 28 minutes because it is a tetrahedral hybridization. So for any sp3 hybridization, the shape is expected to be 109 degree. But we consider it as a planar molecule, and hence we think it is having a bond angle of 120 degree. 120 degree. So as per Bayes strain theory that we will see, the molecule should be bit strained because the bond angle is approximately 10.5 degree larger than the ideal tetrahedral angle. So this planar structure is strained and there is carbon-carbon single bond, so that this cyclohexane molecule could undergo flipping or rotation around carbon-carbon bond without breaking the carbon-carbon connections or cyclic structure, resulting the formation of different conformations. Listen carefully. It is carbon-carbon single bond. So, in cyclohexane molecule, the carbon-carbon single bond could rotate to assume different spatial arrangements, and these spatial arrangements are basically due to the carbon-carbon rotation. And during this carbon-carbon rotation, there is no breaking of carbon-carbon bond. So, the planar structure will rearrange us to many different forms, and they are the conformations of cyclohexane. For cyclohexane molecule, two extreme conformations are identified, and these two extreme conformations are chair conformations and boat conformation. So from a planar structure, the carbon-carbon bond could undergo rotation. Better use the term flipping. Flipping of carbon-carbon bond occurs. As a result, the planar structure gets rearranged to two extreme cases. They are the chair conformation and the boat conformation. In chair conformations, the molecules are arranged in such a way that it looks like a chair. And in boat conformation, the extreme carbon atoms are arranged in such a shape it assumes like a boat. So, the two extreme conformation of cyclohexane are identified as chair conformation and boat conformation. Apart from these two conformations, a large number of other conformations are there, but all the conformation result either starting from chair conformation to ending to boat conformation, or from boat conformation to chair conformation. And these two extreme conformations of cyclohexanes are identified as chair conformation and boat conformation. See here, this is the chair conformation converting to boat conformation, and boat conformation converting to chair conformation due to the carbon-carbon flipping. That means the chair conformation can be converted to boat conformation, and the boat conformation could be converted to chair conformation. And during the conformations changes from chair to boat or boat to chair, a large number of other conformations result in. Some of the important conformation that we meet during the transformation of boat to chair or vice versa are twist conformation or skew boat conformation, half chair conformation. So apart from these twist conformation and half chair conformation, very large number of other conformations are possible, but they are basically less stable compared to boat conformation and chair conformation. So during the transition of chair to boat conformation or boat to chair conformation, it occurs through the formation of twist or skew boat conformation, half chair conformation, etc. You got it? So we could say for cyclohexane, we identify two most extreme stable conformations. They are chair conformation and boat conformation. Apart from these two, there are a large number of conformations, and some of the important are boat conformation, chair conformation, skew boat conformation, and half chair conformation. Take down. Now see the potential energy diagram. When we see the potential energy diagram or observe the potential energy diagram, the chair conformation is having minimum energy. That means maximum stability. And it moves to half chair conformation. And half chair conformation is having maximum energy. Then it moves to a twist boat conformation, which is having a greater energy than chair conformation but less energy than half chair conformation. You just see. Then we move to boat conformation. Basically, boat conformation is having more energy than twist boat conformation. See, 30 kilojoules per mole, but test tubed conformation is having only 23 kilojoules per mole. But we give importance to Bott conformation rather than test tubed conformation. Again, it moves to test tubed conformation in a different plane, moves to half chair conformation, and finally to chair conformation. That means cyclohexane molecule moves from chair conformation to Bott conformation, again to chair conformation, through half chair conformation and twist tubed conformation in different planes. You got it? Take down. See here, in case of Bott conformation, it is having angle strain. The ecliptic strain is also there. Steric crowding is also there. See here, the steric crowding between the extrements. But these strains are not there in chair conformation. In chair conformation, we could say there is no angle strain, no eclipsing strain, and very small steric strain. While for Bott conformation, all these strains are there. So the bond angle, that is the carbon-carbon bond angle, is almost close to 109 degree in case of chair conformation. So the most stablest conformation is chair conformation, which does not have any angle strain, eclipsing strain, or steric strain. A question may come, why chair conformation is most stable? So you should give the answer like this one. Why it is more stable? Because it has a bond angle almost same to 109 degree 5 minutes. That means the angle strain is almost free, no angle strain. And there is no eclipsing strain and only very small steric strain. That is why chair conformation is highly stable. Take down.